Hello guys, how are you? I just wanted to, before talking about McWhitney, before talking about Wilkinson, before talking about non-parametric tests, I had a doubt about how to assess normality because we use non-parametric tests when we have a non-normally distributed data, and we use parametric tests when we have a normally distributed data. But how you assess that normality? That was one of my questions, and that I think that it's important to talk a little about that. So I'm respecting the information that has this forum, it says that you can also discuss here how to assess the normality of the distribution, um, as it is an important decision for the use of a non-parametric test. So I'm going to talk a little about that right now. So basing my thoughts about the last class that we had on Thursday, I took some of the recommendations that the professor gave, and I add some recommendations that I found important on the internet, and there are a lot of tests. There are a lot. I saw hundreds of tests, but I think that these ones are the most important. First of all, seeing the bell-shaped curve of the Instagram, then determine the kernel density estimation. These are two graphics. This graphic. Then we can calculate the skewness and the kurtosis of the data set. Then we can perform an skewness kurtosis test for normality. We can make a quantile plot and see the straight line of the quantile plot. And then if you still has doubts if the if your data is not normally distributed, you can run a Shapiro-Wilk or a Shapiro-Franzen test, right? So these are the tests that are used in order to see if a data is normally distributed. So let's do this test on STATA, and let's see if a data set is normally distributed, right? So here we open STATA. We're going to use a data set predetermined. I found this one pretty interesting. It is named US Life Expectant. No, I'm sorry. It is named TS Line 2 data. We're going to use this one. And I found it very interesting because if we click here, we can see the data plot, the data set. And I found it really, really interesting because we can see how much a person, I don't know who, consume of calories in each day of a year, the year 2002. So let's do everything to test if this data was normally distributed. So first of all, we have to do a histogram. We use here calories as the variable. I'm sorry, this comma is not here, and we write normal. So here we can see the histogram of the data set that we had, and we can see that if I see this, I will say that this data is not normally distributed because there is a little positive skewness to the right, and those are my thoughts, but I'm not a statistician. So maybe you do a histogram and you are still with the doubt if this data is normally distributed. So now what you can do is go here and you're going to do a kernel density estimation, right? That is another graphic test. We can use K density. We use this variable and we write the word normal. So here in the kernel density estimate, we can see how, I think I was right, this data set is not normally distributed because there is a positive skewness, but also I am seeing here something that I didn't see in the last plot, that this graphic is a little more tailed than a normally distributed data, but because remember the red line is normal and the blue line is our data set. So here we can look at the difference between a normal data set and an or data set, right? So now those were the graphic stuff, the graphic stuff. So now we want to use numbers. We want to see numbers if this data is normally distributed. So maybe the first thing that I will do is add more information to that data set. So I'm gonna write some, and I write my variables, and I'm gonna write detail. So now in the calories consumed, we are going to have a lot of information. First of all, the observations. We're going to have 365 observations or all observations in the year. We're going to see the median, we're going to see the mean, we're going to see the standard deviation of our data set. And something that is pretty interesting is the skewness and the kurtosis. So what does it mean? Let's start with the skewness. So if we see the skewness here, okay, if the skewness is zero, we're going to have a normally distributed data. If we have a skewness that is more than zero, we're going to have a positive skewness, skewed data. And if the skewness is less than zero, we're going to have a negative skewed data. So how much is the skewness here? It is 2.3. What that means is that our data set is a little a positive distributed. So we have a positive distributed data set. So now we're going to see the kurtosis. So kurtosis, I have it here. So for STATA, the kurtosis is 3. The cutoff is 3. So if the data set is more tailed, the kurtosis is going to be more than 3. If the data set is less than 3, if the kurtosis is less than 3, or data set is going to be, or I'm sorry, the values are in the middle, or the graph is going to be less tailed, more flat, right? So in our histogram, what we can see, I have here our histogram. I'm sorry, this one now. I'm going to use the kernel density estimate. In our kernel density estimate, what we can see is that our data is more tailed, or the values in the middle are more tailed than a normally distributed data set. So what that means is there are a lot of days that this guy guy or girl, I think that is a guy because he's consuming 3,600 calories, and it is more tailed or data set, right? So that would give us probably more than 3 in our kurtosis. And if we see here in STATA, our kurtosis is 15, 16 also. So our data set is pretty tailed in the middle, right? It's probably not normally distributed, but maybe you still have the doubt. You can run another test for normality, and you can perform a skewness and kurtosis test for normality. The command is skTest. You write skTest and add your variable. And what you are going to see here is that for skTest or skewness and kurtosis test for normality, you are going to see this number. And if this number is less than 0.05, what it means is that our data set is not normally distributed. And if this value is more than 0.05, our data set is normally distributed. So what if we see our graph or data set, apparently because of all the tests that we have done, this graph is not normally distributed, right? So we have still one test to do, that is a quantile plot. Quantile plot is pretty easy to do. Quantile plot, let's add the variable. A quantile plot, what it means is that this is the graph that is supposed to follow our data set in order to have a normally distributed sample. As we can see here, it's not normally distributed. The values are less skewed, that does not follow the straight line that the quantile plot is giving us. So what it says is quantile plot is that our data is not normally distributed. Let's wrap up with the Shapiros. This is the last step. S. Wilk and S. Francia. S. Wilk, sorry, S. Wilk, calories, and S. Francia. We read this the same way as we read the skewness and kurtosis tests. If those tests are less than 0.05, we're going to have a non-normally distributed data. So the Shapiro-Wilk and Shapiro-Francia test told us that this data is not normally distributed. So with all these tests, what we can deduce from our data set, it is that it was not normally distributed. These are all the tests that can be performed in order to test normality, and this is how it is done in STATA, and I hope that this is useful. I think that's pretty useful actually. And if our data set is non-normally distributed, we have to use, in this case, a Wilcoxon test because we are measuring the a Wilcoxon or a Whitney, depending on the categories and the variables and stuff. But in this case, we have we're going to see values within a subject. So I think that is a Wilcoxon. If you are not agree with me, you can comment here in the post below. So thank you, and I hope that this is somewhat useful. Bye bye.